And you can start your presentation. So Rasul was working with me like 2 years, and this like project for 1 year. He has been doing.
Can I share it?
Yeah, start sharing.
Okay, thank you. Okay, hello once more. So as Professor Jonathan introduced before, it's a 1.5 year project, and it's called variable friction sensor for dexterous robot manipulation and human robot interaction. In this presentation, actually, I firstly will introduce to the topic, like state the aim of the project itself, make a small introduction we'll talk about later. As always, did some literature review, stated some state of the art and the current limitations of the current tactile sensors. Then we'll talk about the design of the proposed sensor itself, then move to the results and do some foreseeable conclusion. So firstly, it's important to say how actually crucial for the human itself, the tactile sensing, and also for the robots now, because it is very important for interacting with the environment. And for the most manipulators, they have to deal with, for instance, in industry, with with different types of objects, including the objects that can easily crash and that can slip during the manipulation with this object. And for this purpose, there were developed a lot of different sensors, most of them including force sensors that provide either slip information or force information that shows how strong the object is grasped. But for better manipulation with the object, we need more number of information, including the slip, including the vibration that can caused by the object, the contact between the robot and the object itself, and the force for detection. So the objective of this project is actually to create multimodal sensor that provide several information, including multi-axial force verification. Then we should also verify that the slippage occurs between the object and the robot, and moreover, for secure grasping, we made it possible to slide along the object and grasp easily. Like why it's called dexterous, because it can shift into two different states with a high friction grasp and low friction sliding along the object. I'll talk about and show it in more detail later. So let's firstly review some works that have been done before. There were a lot of sensors that were based on the vibration, and most of them were aimed to detect slippage that occurs when the object is slipped between the gripper of the robot. Mostly they use ultrasonic sound, and there are other works that use PFD sound sensing matrices. So mostly they observe the Fourier transform and also vibrations, and actually this type of method also used in this project. So another works that were based on the vibrations can be seen in these projects. It can be seen that these works shows how the sliding object goes over the vibration over the sensors, and the vibration occurs between them. For example, in one of the works of Irkiblan Salim, they used sensor, vibration sensor accelerometer with a STM that will be also used in this project later. Another methods, another sensors that were developed to sense environmental control of the object is measuring the forces, and they used a lot of different methods, including magnetic, capacitive, piezo methods, and we decided to concentrate on the magnetic task using Hall effect method because this method ensures that there will be less noise between during the sensing because of the low vibration and the high sensing of the magnetic field. So regarding the limitations of some works, the works before that I stated mostly concentrated on one type of sensing one of sensing types, either vibration or the force measurement, while we wanted to ensure more information coming from the object. And most of the sensors that were focused on the development of the multimodal sensors were based on the camera-based methods. The limitation of this type of sensors is that using the camera actually restricts the space that's required to place object. For example, if you want to use the small grippers and the grippers with a very small what's called the space between the fingers, sorry, and there will be a very big limitation. Moreover, the information coming from the camera is very expensive. It's very expensive to process them and store. That's why our goal is to create both a very cheap sensor in terms of the information gathering and in terms of the cost and manufacturing itself. So let me go to the sensor, how we actually designed this sensor and the manufacturing process of this sensor. As you can see from this picture, this sensor looks very simple. It consists actually from 3 parts. The center part is all of them beside the part named C, made of silicon. And the center part is actually a vibration sensor that use accelerometer and to be labeled things are Hall effect sensors that use magnetic force to detect the force changing, and the C is a base that uses that was 3D printed actually to space them in correct positions. And actually this sensor is uses model principle. For example, if one of the sensors is broken, you can easily shift and replace one of them. So going to the starting from the force sensor, let me explain in detail how actually this works. This rendered view of the force sensor. The green thing you can see is a Hall effect sensor PCB. All the transparent part is made of silicon 12 short hardness rubber, and the lower part that's painted by blue is made of short hardness 40 silicon. Actually, this short hardness show how hard is this silicon. The higher the number, the harder it is. Why we made the bottom part from the hard silicon in order to make sure that Hall effect PCB will not be displaced during pressing. So how it works? The golden part is actually a magnet. When some force applied on the sensor parallelly, it displaces it and it comes closer to the sensing device. And by this displacement, we can measure the force changing. Okay, this part of the sensor is actually high friction because the silicon produced has a little abrasive surface because of the molds that was are 3D printed, and these molds are actually abrasive, and due to very high contact space, contact area, it also increases the friction surface that can be created between the object and the sensor. So how we actually manufactured the sensor, that was quite tricky. We built it from 2 different 3D printed parts. We made sure that one of them is actually will be transparent to see the levels of the silicon molded, to be sure that all of them will be equal. So the drawing that you can see is a side view of the of the object that is located on the left. So how we actually made it? Firstly, we molded some very thin layer of silicon with the short hardness of L812. Then we place a magnet on it after it was casted. Then we fill it again with the silicon. After that, that was the most trickiest part because placing the Hall effect on the correct position so it will not be displaced was very difficult as the surface of the Hall effect is not plane. So it sometimes shifted either to the left or to other position, and because of the silicon, which is actually molds from 20 to 40 minutes, it was difficult to be sure that it stays at one position. So we actually made this stick and place it with a tape, two-sided tape, the PCB on this stick, so it will be located on one position. We use this type of cap to be sure that it locates exactly at the center. And as you can see, the holes, these holes are made so we can put a little stick in it, so it stays at the same level in the height level. And we again fill, if you miss it, we again fill it with very thin layer of silicon, so it just enough that Hall effect will be filled. After that, we remove it, then fill it with the rest of the silicon, which is made of sorry, there is a mistake. It's short hardness A14. So this was actually manufacturing process of the for sensors. Now moving for the vibration sensors, they are made of very soft, of two types of silicon. The outer part is made of short hardness 12 also silicon, but a very thin layer that actually works as a shell, to protective shell, to be it cover the very soft silicon gel inside. The manufacturing process was actually a lot easier than the previous one. We used also two molds. In this mold, you can see it's a bottom mold from the side view. So again, we fill it with a very thin layer of silicon of short hardness 12. Then we place the upper one on it, and it created, as you can see, this yellow thin layer, and it casted, and we place it with a bolt, so it will be, but it will not move from side to side, to be sure that this correct layer shell will be casted. After molding, we remove it and place very thin layer of silicon gel. And after that, we place the accelerometer on it. After finishing, it's a lot easy. It's very easy just to fill the covered part with a silicon gel and cover it with a short hardness 12 silicon too. So as you can see on the right side, this the shell that we got for the center part for the vibration sensor of our proposed sensor. So why we actually doing the sensor to be two-parted, and why the center part should be very soft, because it allows us to easily slide the object inside because of the low contact force of the dome format inside sensors. And the accelerometer that we place actually in this dome easily detects the vibration because the silicon gel displays very fastly, and this allows for accelerometer also goes displays quickly. And actually by this vibration we can take two informations. The first one is a moment of contact, surface texture, and the third one is actually slippage. that we'll discuss later. And why we made it also not just soft, that we can make we could actually ease the process and made it from short hardness 12 one monotone layer of silicon, but we made it very soft due to the reason that when we start pressing it, it should displace inside like a human finger. So it pumps in, and this outer Hall effect sensor, actually with a higher friction, allows us to securely grasp the object and sense forces. So using this principle, we actually designed some experiments, and in this section, I will show how we did these experiments and some results we actually acquired from them. So for the experimental setup, you can see we use it we use a UR manipulator that is denoted by the F letter, and we put a shank gripper that allows us to control position and velocity of it, but it was very limited. Then for the verification of the force, we actually used Hall effects, Wittgenstein force sensor. We use it as a reference to see how the force, if the force coming, force information, force pattern coming from the Hall effects will be the true one and the good one. So for the data transfer coming from the sensors, we use the STM32 for vibration sensor. It allows to transfer the data in the frequency of 2000 Hertz. And for the force sensor, we use TNZ as the displacement of the force and transfer rate will not be required so much. But the limitation was 1000 Hertz, but our limitation was set to around 500 Hertz, both of the Wittgenstein and coming from the Hall effect sensors. So as you can see, we actually tested the Hall effect sensors. From this graph, you can see the relation between Hall effect and the Wittgenstein sensors. On the left side, you can see actually you can see on the left side how the pattern following of the Hall effect sensor is similar to the Wittgenstein sensor. The black one denotes how they are pressed, and the blue one is denote how they are impressed. And on the rightest corner, you can see the relation between the Hall effect to Wittgenstein. It's almost 1 to 2. And from pressing and unpressing, you can see the hysteresis of the sensor, like the gap between the pressing and unpressing. This is actually a hysteresis that mostly caused during the deformation and the restoration of the silicon.
Accelerate.
Okay, sorry. So let me go to the experiment. What we actually did, the experiment we wanted to, in one experiment, actually verify sliding, grasping, and slippage. So in the experiments, we press the object until the vibration sensor actually senses the contact. Then we slide along the object with the UR to show that it can easily go up and down while touching it. Then we grasp it until Hall effect sensors sense the force coming. Then we lift it. And after that, we again ungrasp it to see if it can detect the slippage. So for this experiment, we use 3 samples. There are 3D printed 3 objects with which the first one is a plane surface, and the second one is the bump surface, and third one is a cylindrical object. So let me show one demonstrational demo video. So this is a plane object. We put accelerometer on the object so we can see how the acceleration on how actually object did change along the affection of the gripper. So as you can see, we set some threshold manually, and if you pay attention to the low corner, it shows that contact detected while it touched it. Now it can easily slide up and down while still touching it. And now it starts to press it. And you can see from the RKT how the force applied is changing. We wanted to show the acceleration, but acceleration value were very small, and that's why it was and the rate was very high. That was difficult to see from the RKT. Okay, so let me show the results like this, and as you can see from the left picture, this is the actual acceleration accelerometer results. I will show them in detail in the next slides with the positions of the contact slide and the lifting and ungrasping. On the right corner, you can see how the force, the relation of the forces between Hall sensor and Wittgenstein. The pattern of following are similar. So it shows that the grasping of the object was secure, as no change and no high vibrations were seen on this graph. So moving to the detailed observation of the accelerometer results, you can see that at green line, striped line, it shows the moment of contact. After that, it starts sliding, and as you can see from the data from both accelerometers located on the object on the gripper, the red one actually shows the gripper results, and the blue one shows the accelerometer results on the object. As you can see, it shows that it was a contact, and when sliding, both of them were vibrating. That's why it verifies that the contact was there. And after the sliding, it ends at red line, and lifting starts at brown line. At brown line, you can see the spike, how it goes up on the black. Oh, sorry, on the blue graph, which actually shows that the object was lifted. And the very high spike that you can see after that is actually the slippage that shows that. Oh, sorry, the height spike shows that slippage accurate, and as you can see, it falls down very quickly, and the same, the highest position of the spike can be seen also on the red graph, which is actually the result of the accelerometer that was placed on the gripper on our sensor. So this is the same video but with another objects. Should I show you or skip it?
Show, and then we stop. We have 5 minutes for questions. Go.
Okay. So the same process goes here. It let me just quickly yeah, pay attention to the lower part. Yeah, it's contacts, it sends contacts, and it goes. And the most interesting part here is that we assume that there will be more vibrations due to the bumps, but due to the fact that the bumps were located outerward by 2 millimeters, the very slight contact was sensed by the accelerometer, and that's why it didn't go deep enough to have very high vibrations, and that it lifts it again. Let me just skip it. Okay. And you can see the graph here too. Okay, the same procedure was performed by the cylinder, and as you can see, there were also the similar results that shows how the grasping was secure, and the vibrations occurred during the sliding and the lifting, and the slippage was detected. So let me show you one more experiment. This the human robot interaction application of the sensor. So in this video, it can be quite difficult to understand what's happening. So I'll explain it during the video. So actually, sorry, what we were doing is that when we slide inside the stick, the gripper due to vibration should sense it and should close it, and when we put the stick on the other direction, it should ungrasp it, like it should respond faster, response times by this increase higher, and when we try to slip it very quickly, it should grasp it too. So let me show it. So I goes inside, and as you can see, it grasps, and when I go another direction, it ungrasps. and I try to sleep it. Right now, let me show it. And I'm slipping it back to the limitation of the speed of the gripper. It couldn't respond quickly. Okay, that's it. So let me give a conclusion. So actually, we achieved the aims that we included in our objective. We verified that the forces and the grasp verification can be easily measured by this sensor. That we can detect slippage, enforce sliding, and manipulation with the
time. It's okay.
continuous objects.
Yeah, you can go next slide. Thanks. And then
Okay, I want to actually acknowledge all the technical lab members actually who helped me during the work, and especially to Mulder, Toljan, and Rustam, who really contributed to this project. And thank you too for professors for your help and feedback, and for attending this presentation. Okay, thank you.
good, very good. Okay, I liked it, but let's see, Carlo and Matteo, who would you can start.
Oh no, if you want, I can start. I very brief
Okay.
questions. One observation, after a while, I was thinking, wow, this is still slide number 3. So just I noticed that all slides were slide number 3. Then I realized,
sorry.
no, okay. No, don't worry. It's just funny thing. No, I think it was a very good presentation. I mean, very good work. I mean, I'm, as you know, more a theoretical person, so I'm always fascinated by how people can build something that's practical, that works for real. And I think it was very good, especially the description of the force sensor when you showed the different parts, one, the other, etc. That was very, very helpful to understand the process. I just have a general question. So the work is about human-robot interaction. At the end, you showed how you can pass this object slide and it will grasp it. How do you see that this could be applied to, I mean, where do you see this applied in some practical application? I mean, can it be this, for example, in the field of manufacturing, if you need to pass an object to a robot, or more about doing a task together where the person does something and the robot, or it can be in different fields, robots for, I don't know, assistance of elderly people. I don't know. How do you see this type of applications being applied in some domain?
Personally, I saw it in the fields where it's required to actually transfer the object, which is very that can easily crack, and this sensor allows actually sense the slippage, so it will not fall down and crack. And due to the very the bumped part, it can grasp it very softly. And by knowing the fact that the vibration occurs not high enough, it can grasp it slowly, slow by slow, while ensuring the grasp during it. So mostly manufacturing of the very fragile parts, and maybe in medicine when, for example, in assistive medical robots, when you try to help with objects that will not slip down when during the operation, or when you transferring from a doctor, for instance, when you're giving the instruments to the doctor.
Okay. All right. Thank you very much. That's all from me.
So for fine manipulation, good. Thanks.
All right.
Yes, Carla. Yeah.
Can I?
Yes, Carla.
Before, actually, I would like to ask just one simple question. But before to do that, I would like to give you some suggestion. Okay. The presentation is nice, actually, with small defect that it happened because probably you are not very used to do this kind of presentation. First of all, you need to find a way to be to summarize what you want to say, because most of the time in the conference and so on, you don't have so much time. So you need to find a way to communicate content without spending so much time in slides. Okay. The introduction was okay, but the literature review, basically you spent 3-4 slides without any plot, any graphical effect, and just writing something, and it was not clear at the end. I didn't really understand which kind of vibration sensor are on the market, which one are under study, and so on. Instead, one plot, a table that show simply what the market offer and the research is researching in this moment would have been more effective. Other things actually also Matteo told you need to number the slide, because if we want to return back to see a slide, I cannot, because I cannot tell you the number. I cannot. But
you can ask
nevertheless,
him that you had a doubt on slide number 3.
Exactly, number 3, please. Okay. That's it. Actually, this is just the thing that, in my opinion, you should fix. After that,
sure.
I really enjoy also the graphical part, the video, and so on. I would like to ask you one simple question. Can you return back on the slide number 3, where you have the model, actually, where you show the model of your sensor, you know, with the cap in the middle for vibration and the force sensor on the side.
Sorry, I guess it's...
Yeah, I need another one. Okay, another one.
This one, yeah?
This one. Actually, I'm asking how big it is. That's important, right? Because suppose that I want to use not one, I want to use 2 or 3. Suppose that I want to do something more complicated. How big is this sensor?
I can show it if you want.
No, like give me the size. Don't show me. Give me just the size, more or less, roughly.
It's just like this. Like it's 10 centimeters, I guess, in long, and like 5 centimeters in width.
My second question is: can be done smaller? Can be created smaller?
Actually, I guess it can be done smaller.
All right. So move some slide on forward. Regarding the force sensor, actually, during the description of the maybe the next slide where there is the description of how you beat this one exactly. You said several times, and I really didn't understand. You talk about the surface of all effect. Can you explain what does it mean? Because I didn't really. What is the surface? What is the surface of all effect?
So let me explain from this slide. As you can see, from the picture on the upper half of the slide, as you can see, the surface of the Hall effect sensor is not
because you
plain,
didn't say sensor. So it's the surface of the Hall effect sensor.
Yeah, sure.
All right, sure. People is not in the area remain a little bit. Let's say, what is the surface of our effect? All right. Another thing, and just after that, can you move forward? Actually, when you have the plot, if I remember, of force sensor with the graph. Move.
This one.
This one. Actually, the one in the middle is written time versus Hall effect. But honestly speaking, I can see Hall effect on one side, and on the other side, I can see the formation.
Yeah, it's true. It's just my mistake. Yeah, I'm sorry for this one. I didn't pay attention to this.
All right. So, nevertheless, I enjoyed the results. Very, very, very beautiful. I have to be honest. I enjoyed a lot. And I have also to tell you one thing. I prefer the presentation in general. Is more descriptive, is more complete than the report. The report actually were done, I should say, a little bit, I mean, too fast. you explain better during the presentation. Usually it's the contrary, because the report actually you have all the space that you want to explain. But here you have done a very good job. Yeah. Thank you.
Thank you too.
Good. Carlo, really thanks for this feedback. I will keep this track for future students. Okay.
Thank you. Thank you very much. Yeah.
And Matteo, thanks. Good.
No problem. Thank you. So how should we proceed now? We need to fill the report for the presentation, right?
Yeah, I prepared these Google Forms with filled up your names and then ID and Rasul's ID number name. I can send you the link again. It's a Google.
But that's the actual.
I already have the form. I have just to finish to fill it.
Then if you can send it, I can. I will. Or with Tutahit, I think we need to send it. You can send it to me or.
Okay.
Be simple because I have
I will
idea
send you
what
this
to
link.
say.
Okay.
All right.
Okay. Perfect.
Thank you a lot, Rasul. It was a good
Thank
work.
you too. Thank you too.
I hope we will publish this work. Yeah, Rasul.
Sure. Yeah.
That was it.
All right.
Bye bye.
So
Thank to everyone. I'm leaving.